Hi, today we're going to talk about cosines. The generic form of a cosine is x of t equals k cosine omega t plus phi, which we can also write as k cosine 2 pi ft plus phi. Let's focus on the second one first. So there are three basic parameters. There's the amplitude k, there's the frequency f, or alternately you could say the frequency omega. We'll talk about both of those. And then the final parameter is the phase shift phi. Okay, so k tells you how big your amplitude is in the vertical direction, the y-axis. The frequency tells you how fast, how long it takes to complete one cycle, essentially. And then phi tells you if there's any left or right phase shift associated with the signal. So let's start with k. We said k is our amplitude. And generally speaking, it is unitless. Our frequency f is in units of cycles per second, which is otherwise known as hertz or Hz. And then our phase shift is, sometimes we call it phi, sometimes we call it theta, it doesn't matter. That's in units of radians. And it tells us the phase shift. All right. Now in addition to that, you can see that we have the parameter, the variable t, that's our independent variable. That's time. And generally speaking, that's in units of seconds. And then finally we have the constant 2 pi, and 2 pi is a constant. Let's try that one more time. And it's in units of radians per cycle. And that shouldn't be too surprising. If you cycle all the way once around a circle, that's 2 pi radians. So that's where that comes from. It's a constant. Now, you can only take the cosine of radians. Okay, you can't take the cosine of any other unit. So if you look at what's going on inside the parentheses, in both cases, phi is radians, so that's good. And then the other term, omega, is radians per second, and t is seconds. So when you multiply those, you just get radians. So I should probably point out that the frequency omega is in radians per second. And that's also a unit of frequency. It's an alternate, it's like an alternate unit basically. Okay, and if you look at the 2 pi ft, 2 pi is radians per cycle, f is cycles per second, so the cycles cancel, and you're left with radians per second. And then times t, the seconds cancel, you're left with radians. So radians plus radians, you have radians, and that's good. You can take the cosine of that. Excellent. So let's go ahead and do an example and see if we can extract a value for each of those parameters. So let's go ahead and paste in a picture of a cosine and try to get all three values. So the first thing, the easiest thing to do is that we can just read right off the graph, we can read the value of k. So k is the amplitude. It tells you how big the signal is, and in this case it's relatively straightforward. K is 0.3, and again it's unitless. Good. The next thing we need to figure out is the frequency, and in order to figure out the frequency we need to look at the period. So that's actually a unit that we haven't talked about yet. So the period is how long it takes to complete one cycle, and that's in units of seconds. So the conversion is that the frequency in hertz is the reciprocal of the period. Okay, if your signal takes 1/10 of a second to complete one period, then in 1 second you'll have 10 hertz, 10 cycles, so they're reciprocals. And then we also know that omega equals 2 pi f. I'll just put all that together in one place for completeness, which is 2 pi over t. Okay, those are all equivalent. Good. So let's go ahead and start by measuring the period. So I'm just going to eyeball it off the graph. I don't need to be too exact for the purposes of this exercise. So the period is peak to peak time, and looking at my picture, I can estimate that that's about 4 divisions, 4 hashes, maybe a little more. Let's see, 1, 2, 3, 4.5. Okay, let's call that about 4.4 cycles. Sorry, about 4.4 divisions, and I can see down here that each division is a millisecond. So about 4.4 milliseconds, which means that the frequency is 1 over 4.4 milliseconds, which comes out to 227 hertz. Now, the last thing we want to do is solve for the phase shift phi. And in order to get that, we're going to solve for the time shift first. So let me show you how that works. So let's do a little intermediate calculation. If we have a cosine that's k cosine 2 pi ft plus phi, and we want to solve for phi, an easier way to go about doing it would be to factor out the 2 pi f from the two terms inside the cosine. So that'll be t plus phi over 2 pi f. And in doing so, the 2 pi f is going to be our time shift. And that shouldn't be too surprising. We know that for any function, let's say you have some generic function f of t, if I turn around now and give you f of, let's say, t minus 3, you know I'm talking about the same signal f of t but shifted to the right by 3 seconds. And that's exactly what's going on here. So the time shift is going to be equivalent to phi over 2 pi f. So I'm going to come here and I'm just going to see if I can eyeball about how much time shift we have. And it looks like it's a little less than half a division. Let's just call it half a division to be to keep things straightforward. So the time shift is going to be minus 0.5 milliseconds. And that minus is because it's a right shift. And I'm going to set that equivalent to phi over 2 pi times 227. And now I have everything I need to solve for phi. So I go ahead and whip out my calculator and I get that phi equals minus 0.7 radians, which is about equal to 0.23 pi. Okay, and there's no rule that says you have to convert it into multiples of pi. It's just convenient sometimes. Now, a quick sanity check you can do to make sure that your answer makes sense. We know that 2 pi radians gives us 1 complete cycle. That's a constant. In our case, we have 0.23 pi. So we can cross multiply in order to figure out how many cycles we're talking about in this case. So if we cross multiply, we have 0.23 pi over 2 pi, and that's going to give us about, I'm going to estimate here, about 0.11 if you want to be exact cycles. Okay? So we have just over 1/10 of a cycle. And if you look at that, it makes sense, right? If you compare the time shift over here shown in green to the entire duration, it's about 1/10 as big. So that's a sanity check that we did it right. So finally, putting it all together, we have the equation for this cosine is x of t equals 0.3 cosine 2 pi 227t minus 0.23 pi. And there you go. Now, if you want to practice, let me give you another cosine and see if you can figure out what the plot should look like. So what if I gave you another function, y of t, and let's have it be something like 0.7 cosine 500t minus 0.9. Let's try that. Okay, so a good practice would be to take this function y of t and see if you can use the same steps that we've used above to sketch what the plot of that might look like.